Good day, everyone. We'll be considering Fourier series in this lecture. Now, given an LTI system, say S of t, fell into an LTI system characterized by h of t, then the response is the convolution between the system impulse response and the input S of t. Here we have that the output y of t is represented by the convolution sum or integral to be the linear combination of some shifted impulses. That is, the convolution integral taking limits from -infinity to infinity, h of tau, s tau, s of t minus tau, the tau, the s of t minus tau, are some shifted impulses. So, when the eigenfunction s of t is the same as est as previously defined, we observe that the convolution sum reduces to the sum of the weighted complex exponentials. That is, y of t is the same as integral infinity to infinity h of tau t minus tau, tau, just like as we showed earlier, this reduces to est h tau epsilon times st d tau, which is the same as h of s st. Here, s of t is given as the eigenfunction of the system. This is the representation in continuous time. Okay? Continuous time systems. While in discrete time systems, we represent the eigenfunction as z of n, for which z to the power of n is the eigenfunction, which is in the discrete time system. Should note that s and z are complex numbers. Now, from this deduction, we can therefore conclude that y of t is the same as hs of s. h of s est, continuous time, while y of n h of s z to the power of n in discrete time, and here h of s, and this is h of z, sorry, this is h of z, h of s and h of z are the system response for the discrete time, for the continuous time and discrete time respective. Okay, for the continuous time and discrete time perspective. This. Now you should note here that h of s and h of z are the complex amplitude. Complex amplitudes and are also the eigenvalues corresponding to the eigenfunctions. St and Zn respectively. So the complex amplitude, which is the same as the system response, is therefore h of s negative infinity to infinity, the convolution integral, the convolution sum, h of tau, so on star tau is the Laplace transform of the system. As we saw earlier. Now, in a similar vein, since Zn is a complex exponential sequence, therefore, for the discrete time system, I have y of n to be the same as the sum for k taking values from negative infinity to infinity h of k x of n minus k. Okay, now recall that s of n is the same thing as Zn, so s of n minus k be the same as Zn minus k. So once we plug that in, output response reduced to k Zn minus k, which is the same summation. For k taking an out from negative infinity to infinity, for k infinity plus infinity, h of k Zn minus k. Now, this is the form h of Zn. Okay, where h of z is the same as the summation of h of k z is k, for k taking on values from negative infinity to positive infinity is the z transform, okay, which is equivalent to the Laplace transform in the continuous time domain. Laplace transform, while in the discrete time domain, this is the z transform. So h of z, once again, is the eigenvalues associated with the eigenfunction z sub n. Eigenfunction z sub n for specified values of z. So, in general, a signal can be decomposed in terms of the eigenfunctions. Okay, so for instance, if the input signal s of t is a linear combination of complex exponentials, then it means that s of t is the same as a sub 1 es1 of t plus a sub 2 s2 of t s2 plus a sub 3 es3 of t all the way to a sub n esn sub t. So meaning if a system is fed with an input a sub 1 es1 of t, for instance, characterized by h of s1, then the output, the a1, h of s1, es1 of t, and the same applies till an esn sub t is fed into the system, for which system is characterized by h of sn, then the output of an, h of sn, esn t. So by superposition, the sum of the responses will now be y of t, the same as a1, h1, hs1, es1 of t, plus a2, s2, es2 of t, all the way plus an, h of sn, esn of t. And so, in general, y of t can be described as the sum a sub k, h of s of k, esk of t, taking on some finite values, continuous time domain, and then y of n can take on values such that s of k, h z sub k, z sub k of n, the discrete term. So note that the h of s sub k and the h of z sub k are the Laplace transforms and z transform respectively for the continuous time and discrete time sequence. So when the Laplace transform, note, when the Laplace transform is evaluated along or over the j omega axis, that is, we have the s-plane, sigma, j omega. So when the Laplace transform is evaluated along the j omega axis such that sigma is equal to 0, then s, sigma plus j omega, will be equal to j omega. Sigma reduces to 0, that is the damage factor reduces to 0. So, if this happens, then the Laplace transform converges to the Fourier transform, such that s tends to j omega, then est tend to ej omega. So there we move from Laplace transform to Fourier transform. And in the discrete time domain, z is the same as epsilon j omega n. Okay? Good. So in other words, now that we have progressed into the Fourier transform, then y of t will now be the same as h of omega, ej omega t. Now note that the Fourier transform of an a periodic signal is a continuous function. So, for a periodic signal, the Fourier transform is a continuous function. Okay. Where x of t is the same as ej omega t is an aperiodic signal. Okay. But when the signal is periodic, so let us take a look at this. When the signal is periodic, the Fourier transform is a discrete function. Okay, so take note. Now the Fourier transform of an aperiodic signal is a continuous function, while the Fourier transform of a periodic signal is a discrete function. Now, since discrete functions are represented by discrete set of numbers, it is logical to talk in terms of series because they are not continuous. Because at this point, we begin to talk in terms of discrete values. Plus 1, plus or minus 2, plus or minus 3. So since we have a series, this therefore leads us to Fourier series. So hence, the Fourier transform of a periodic signal converges to a series of frequency contents that are represented by discrete set of numbers k. This series is referred to as the Fourier series. So in other words, when we take the Fourier transform of an aperiodic signal, then we have a continuous function, and then we say that is Fourier transform. But when we take the Fourier transform of a periodic signal, because of the fundamental time period, we see that the frequency contents are represented as a set of discrete numbers. And all we can then talk about is the linear combination of these frequency contents, which are of discrete sets from probably 1, 2, 3, 4, 5 in terms of their harmonics. And then all we can talk about is Fourier series. So, Fourier series is therefore Fourier series is the outcome of the Fourier transform of periodic signals. So, given a periodic signal, say S of t, minus S of t plus t, for all values of t, where S of t take on some positive values of t, capital T, then the fundamental time period T naught of S of t is the minimum positive non-zero value of t. That is the positive zero value t, such that omega naught is the same as 2 f naught is the same as 2 pi divided by t naught, where f naught is the fundamental frequency, t naught is the fundamental time period, this is the fundamental time period, f naught is the fundamental frequency in hertz, and omega naught is the fundamental angular frequency in radians per second. So, a periodic complex exponential signal therefore becomes S of t is the same as epsilon j omega naught t, which is the same as epsilon j 2 pi t naught t, and is the same as epsilon j 2 pi f naught t. Okay, and since the Fourier transform of a periodic signal is a series of frequency contents represented by a discrete set of numbers, as we mentioned earlier, it suffices to say that the signal is a set of harmonically related complex exponents. Say phi of k of t is the same as epsilon j k omega naught t, which is the same as epsilon j k 2 pi t naught t for values taken from k, 0, ranging from 0, positive 1, positive 2, all the way. So hence, each of the signals has a fundamental frequency that is an integral multiple of the fundamental frequency of omega naught. That is, for k equal to 1, then phi 1 of t is the same as epsilon j, that's 1, omega naught t, where omega naught is the first harmonic. First harmonic or fundamental constant. Okay? Then for k equal to 2, you see phi of 2 of t is the same as epsilon j, k is 2, 2 omega naught t. And here, 2 omega naught is the second harmonic. And when k is 3, we have the third harmonic, the fourth harmonic, all the way to k equal to n, and then we have phi n of t, the same as epsilon j n omega naught t, where n omega naught is the nth harmonic. Okay. So from this deduction, we can therefore say that the linear combination of the harmonically related exponents is of the form, so let's put that down, the linear combination of the harmonically related components of form S of t, the same as summation k infinity, infinity, so k epsilon j k t, which is the same summation k to infinity to infinity, so k epsilon j k 2 pi t naught t. Now this is the Fourier series. Now, if we take a positive value of k, this negative infinity to positive, let's say we take a positive value of k, then the Fourier series can be rewritten as S of t is the same as k equal to 0 to infinity S of k epsilon j k omega t. And when k is equal to 0, then S of t is the same as k 0 to put out the summation anymore. K equal to 0, so that a naught epsilon j, 0 times this is 0, so the whole process here reduces to 0, and we know this epsilon 0 reduces to 1, so that will be a naught dot 1, that will be a naught. So at k equal to 0, then this expression reduces to a constant. Better still, a DC value. Okay. Then the Fourier series can now be rewritten as S of t is the same as a naught plus summation k equal to 1 because it's normal from 0 because a naught dot 0 plus summation from k equal to 1 to infinity, then S of k epsilon j k t. Good. And this, by expanding the exponential function, which is the sum of sinusoids, then this expression is the same as a naught plus summation k equal to 1 infinity, so k cos k omega naught t plus j sine k omega naught t. So therefore, S of t is the same as a naught summation S of k equal to 1 infinity cos k omega naught t plus summation k equal to 1 to infinity j S of k sine k omega t. Now, if we take a sub k to be equal to a sub n, then j a sub k equal to b sub n, and technically k is the same, then k is the same as n, and we can write the Fourier series to look something like this. S of t is equal to a naught, which is the PC value, n equal to 1 infinity an cos n omega naught t plus summation k equal to 1 infinity jk is the same as bn sine n t. Here, see that a naught, an, and bn are the Fourier coefficients. The Fourier coefficients. You have to figure out how to estimate. Okay. Now, this expression is the trigonometric form of the Fourier series. So, since S of t is a periodic signal, the area under the graph of the signal can be evaluated by integrating over one fundamental time period. Good. So, for us to evaluate the coefficients, a naught, an, and bn. Now, recall that the Fourier series, so first thing we want to do here is an, right? Good. Now recall the Fourier series is given as S of t, a naught, plus summation, an, n, t, n, for the 1 infinity, plus summation, infinity, en sine t. So if we integrate both sides over one fundamental time period, so to evaluate a naught, integrate both sides over fundamental time period such that the integral from 0 to t naught of t dt is the same as integral a naught dt 0 to t plus integral 0 to t summation an cos n t dt to infinity plus summation 1 to infinity en sine n n t. Now, recall that the integral of a sine or cosine over one fundamental time period is 0. Okay? Because once that is done, say for instance, you integrate sine, integrate your sine, then you're going to get your cosine, for instance, and once you take the limit over one fundamental time period, and you say it reduces to 0. It reduces 0, it reduces to 0. So therefore, integral 0 to t naught s of t dt is the same as a t taking up limits from t to 0. So this is a constant, so it comes out. So that is a naught. Then the integration of a naught becomes a naught t, taking that t to t naught. T naught. So this therefore is the same thing as a naught t naught 0, which is called a naught t naught. Good. So a naught is therefore the same as this integral divided by t. So that will be 1 over t integral 0 to t naught s of t dt. So the next point now is to estimate s of k. Let's split the screen. Now, to evaluate s of k, once again, recall that our s of t is the same as a naught summation an cos n t plus summation bn sin n t. Okay? So n equal to 1 to infinity. So to estimate s of k, let's multiply through by cos n equal to t. Okay, so it means that s of t cos n omega t is equal to a naught n omega t plus summation a naught cos n omega naught t times cos n t plus summation en sin n t cos n omega t. So this now is expression reduced to cos squared n omega t, right? So we can now integrate both sides, integrate over one time period, fundamental time period. Okay? Once we do that, it's 0 to t s of t cos n t is the same as integral a naught cos n t to t integral 0 to t summation of an cos squared n omega naught t dt dt is for n equal to infinity plus integral 0 to t summation of n equal to 1 to infinity dn sine n omega t plus n omega t dt. Okay. Now, just like we established earlier, this reduces to 0 and this reduces to 0. Well, we don't know what this function is, so this may not reduce to 0. So what we now have is integral 0 to t s of t cos n omega naught t dt is the same as integral 0 to t an cos squared n omega naught t. Okay. Now, okay. Now, recall from trigonometric identities, trigonometric identity, that cos squared n omega naught t plus sine squared n omega naught t is the same as 1, such that sine squared n omega squared n omega naught t will be the same as 1 minus cos squared n omega naught t. But cos 2 n omega naught t is the same as cos squared n omega naught t minus sine squared n omega naught t. Okay, so if we substitute for the sine squared component, if we plug this to this, so that will be cos 2 n omega naught t is the same as cos squared n t minus 1 minus cos squared n omega t. Right? So this is going to give us cos 2n omega t is the same as cos squared so let's just compress this. So minus times minus is plus, so we have 2 cos squared n minus 1. So that will give us is the same as 2 cos squared n omega t minus 1. So this will be the same as 2 cos squared n omega t is the same as 1 plus cos 2n omega t, such that cos squared n omega naught t is the same as 1. 2 divided by 2, 1 plus cos 2n omega t. So if we integrate this, if we plug this into this expression, so it means that cos squared n omega naught t is the same as 1 over 2 into bracket 1 plus cos 2 n omega naught t. Okay, so once we plug in that parameter, then we should be able to integrate this entire process. So that is 0 to t s of t cos n omega t dt now is the same as integral 0 to t an dot 1 over 2 1 plus cos 2n omega naught t. So this is going to give us, time we integrate, we'll bring out all of this. So that's an over 2 into bracket is integrate t, 1 that is t plus cos 2n omega naught t will give us sine 2n omega naught t divided by 2n omega 0 to t. And once again, this reduces to 0 over 1 fundamental time period, such that we now have an over 2 into bracket t 0 to t. So which will give us t minus 0, that is t, that is an t, t naught, sorry, it's t naught, right? It's fundamental time period. Fundamental time period. T naught. Okay? It's the fundamental time period. T naught by the 2. So integral 0 t naught by this one. We bring this down. S of t cos n omega t dt is equal to a naught an, sorry, t naught divided by 2. So if we multiply through by 2, that is 2, and we divide all by t, that would be t naught integral to t naught s of t cos n omega naught t dt is the same as an. Okay, so what is left? Bn. So to resolve Bn once again, recall that S of t is the same as a naught plus epsilon an cos n omega t is summation Bn sine n omega t. For n equal to infinity. Okay. So the first thing is to multiply through by sine omega t. So multiply through by sine n omega t. So when we have s of t sine n t a naught sine n t summation an cos n omega t sine n omega t, so n 0 to infinity, plus summation bn n to infinity sine n omega naught t times sine n omega t sine squared n omega t. So the next thing is to integrate, right? To get the value, the area under the graph. So we integrate through, integrate over, sorry, integrate over one fundamental time period. Okay, so that will integral 0 t naught s of t sine n t to a naught integral to t naught sine n, sorry, dt t dt integral to t naught solution 0 infinity an plus n t sine n t plus the integral 0 to t naught summation n to infinity bn sine squared t t t. Okay, so once again, this reduces to 0, this reduces to 0, but we don't know what this value is, we don't know the scaling parameters here, we don't know what they are, so that will alter the sequence. So we have 0 to t naught, s of t, sine n omega t, the same as integral 0 to t naught, summation n to infinity, n sine squared, so this n, right? N t t. Okay. So once again, from the trigonometric identities, we have cos 2n omega t is the same as cos squared n omega t minus sine squared n omega t, such that cos 2n t same as sine squared n t sine squared n t, just 2 sine squared n t and cos 2n t is equal to sine squared n t. So sine squared n t the same as 1 over 2 minus cos 2n t. So once we plug that into this parameter, so in other words, we're going to get integral t naught 0 to t naught s of t sine n t dt. This is dt, please. So integral 0 to t summation n to infinity en dot 1 over 2 minus cos 2n t dt. So this is going to give us n dot 2 to brackets 1 minus sine 2n omega t divided by 2n omega naught 0 to t. So this again reduces to 0. So we have en to t naught, right? This is t naught. So it means that integral 0 to t naught s of t sine n omega t dt is equal to this. So t, so bn is the same, multiply through by 2 here, then divide through by tn, so that by t naught, then integral 0 to t naught s of t sine n omega t dt. Perfect. now that we have established that, so in summary, we can now identify the coefficients. So in summary, the trigonometric Fourier series. So we have one, the trigonometric Fourier series. So the form investigated so far, A0 plus summation infinity an cos n c n equal to 1 infinity en sin n t, where a0 is the same as 1 t0 integral 0 to 1 greater than time period of t dt, then an same as 2 over t0 to greater than time period of t plus n t t bn is the same as 2 over t0 integral 0 to t0 of t sin n t t. And then some assignment, you want to work it out, the magnitude phase form of the Fourier series. So the magnitude phase form of the Fourier series is given by s of t a0 summation to infinity cn cos n t plus by n. The third is the complex exponential form of the Fourier series is given by s of t, same summation of n equal to infinity to infinity s of n, which is a complex number, epsilon jn minus t. Okay, and s of n is given as 1 over t0 integrated over 1 time period, x of t epsilon minus jn negative t dt. And note that s of n is a complex number. Okay, now the relationship between the forms Fourier series is given by now S of n is the same as 1 over 2 an minus bn. An minus bn. So once the trigonometric Fourier series coefficients have been evaluated, then we can estimate for Sn. And should we have the parameters from the magnitude phase form, then S of n is the same as 1 over 2 Cn epsilon j phi n. Okay? And then also A naught is the same as x naught. Then An is the same as 2 times the real value of S of n. Recall that S of n is a complex number. Okay? While Bn is the same as minus 2 times the imaginary value of n. And also Cn is given the square root of an squared plus bn squared. An squared plus bn squared of phi. Because here we have the plus sign. So this is going to be minus tan inverse bn. So should this be minus, then we don't need, should this be negative, then we don't need this negative sign. Good. Now that we have discussed all of this so far, for a periodic signal to have a Fourier transform, or a Fourier series rather, sorry, well, Fourier series is the Fourier transform of a periodic signal. Okay, so for a periodic signal to have a Fourier series, it should, to some extent, satisfy the Dirichlet conditions, okay? Dirichlet conditions. So in other words, these conditions are sufficient but not necessary, okay? So the first of it is that the signal S of t should be absolutely integrable over one fundamental time period, okay? Over the range of the time period. That is integral over the fundamental time period of mod S of t should be finite. And the second condition is that the signal S of t should have finite discontinuities. Finite discontinuities over range of time period. So in other words, if we have a signal, say something like this, this is t naught, and this is 0, so this is one discontinuity, this another discontinuity, this another discontinuity. So we have 3 discontinuities. So it should be fine. Okay. And the third point here is that the signal S of t should have finite number of maxima and minima over the range of time period. This for the same signal, this is T naught, this is 0, well, this is a maxima, that's 1 maxima, and this is a minima, so it has 1, right? So it's finite. Okay. Now, how do we estimate the energy content? Energy content of a periodic signal. Estimate. So, well, this brings us to the Parseval's theorem. And what the Parseval theorem tries to establish is that we try to equate the energy of the signal in the time domain to the energy of the signal in the frequency domain. So in other words, Parseval's theorem states that the energy of a signal in the time domain is the same as the energy of the transform signal in the frequency domain. Just this. So in other words, all that Parseval's theorem explains is to equate the average energy divided by the fundamental time period. So it's equate the average energy in the fundamental time period of the input signal with its frequency, with its energy in frequency domain. So let us look at a few examples before we call it a day. So the first example, so let us verify Parseval's theorem for Fourier series. So we already know average energy in time is the same as the energy in the frequency domain after transformation. So recall we gave 3 forms of Fourier series: the phase magnitude form, the trigonometric form, and the complex exponential form. So if you recall, let us strike the line here. If you recall the complex exponential form of Fourier series, that is S of t, is the same as the sum n equal to infinity, S of n, epsilon j, and t. So the complex conjugate we yield, so if we take the complex conjugate of this, we yield summation n equal to infinity S of n, so j and t is conjugate will result in a reversal of time. So we'll have summation n infinity to infinity is conjugate of n epsilon, so there'll be reversal in time, so we'll have negative here j and t. So in other words now, S of t, let us still explain this. Now that we have S of t and the conjugate, so if we estimate the average energy value, then it means we'll multiply both and integrate over the fundamental time period and divide by the fundamental time period. That is, we'll have 1 over t naught integral 0 to t naught S t conjugate S conjugate t dt will give us sum of this expression here, and for the negative infinity to infinity n epsilon j t, and then the conjugate n infinity to infinity S conjugate of n epsilon j t. So we have the same limit, so can replace with a single one, and negative infinity to infinity of n times this conjugate of n epsilon j n t epsilon minus j n t. So if we compress further, so this is going to give us summation n infinity to infinity n S conjugate n epsilon j n omega naught minus n omega naught t. So n omega naught minus n omega naught will reduce to 0, right? So that is 1 over t naught integral 0 to t naught x of t is conjugate of t dt. Then we have 1. So this times this is s squared. So t naught 0 to t, that will give us the mod of s of t squared dt equal to summation of n equal to minus infinity to infinity. That will give us the mod s of n squared epsilon 0 and this will reduce to 1. So 1 over t naught integral 0 to t naught s of t squared dt is the same summation of n infinity to infinity s of n squared QED. Okay. So let us consider one Fourier series example, and we leave major practice to the candidates. Okay. So let us assume we have this signal. This is 2 pi, this is 4 pi, this is t, this is 1, then this is s of t. Okay, this is 0. So from here, using the equation of a straight line, y is equal to this number, y is s of t, right? Okay. So we have s of t is the same as mt plus c, but here the intercept is 0. So this is 0. So n is the same as s of 2 minus s of 1 divided by t of 2 minus t of 1. S of 2 is 1 minus 0 divided by t of 2 is 2 pi minus t of 1 is 0, which is 1 over 2. So s of t is equal to 1 over 2 pi times t or 0. So that will give us t over 2 pi. So the equation that describes this expression is s of t equal to t over 2 pi. Okay? So let's put it here. S of t is equal to t 2. So let's write all of this. Now that we have done that, we need to evaluate the Fourier coefficients A0, B, AN, BN, and then establish the series, right? So let's see. Now A0 is the same as 1 over T0 integral 0 to T0 s of t dt s of t dt, right? So t is 2 pi, right? 2 pi. So this will be the same as 1 over 2 pi integral 0 to 2 pi. S of t is t over 2 pi dt. So this will be this times this, that will be 1 over 4 pi squared integral 0 to 2 pi t dt. This is going to give us 1 over 4 pi squared divided by t squared over 2, 0 to 2 pi. Okay? And this will be 1 over 4 pi squared to bracket 2 pi squared, 2 minus 0. So this will truncate this will truncate this. This is 4 rather than 4, right? t squared, 2 pi squared, 4 pi squared. Okay, 4 pi squared. Okay, divided 2 pi. Same divided by 2. Divided by 2. 2, 0. Okay, so this will truncate this. So A naught is the same as 1, 2. Now, Bn, or An rather, is the same as 2 over T naught, integral 0 to T naught, S of T cos n omega naught T, T. But omega naught is the same as 2 pi over T naught as 2 pi over 2 pi is equal to 1. So An will therefore reduce to 2 over T naught integral signal 0 to T naught S of T cos nt dt. So for S of T is T over 2 pi, so An is equal to 2 over 2 pi integral 0 to 2 pi T over 2 pi cos nt dt. So 2 truncate 2, so that will be over 2 pi squared integral 0 to 2 pi t cos nt dt. So this can be solved using integration by part method, okay? Such that integral of uv dx is the same as u integral v dx minus integral du dx integral v dx dx. So once we do this, what are we going to get? So let's bring this out. So integral, okay, let's do that. Integral t cos nt dt u, that is t integral v cos, this is u, this is v cos nt dt minus integral u is t, so du will be dt, it's the s dt here, then, that's dt in our case, the s is dt in our case, then v is cos nt, then dt, everything is dt. So in this case, this will be equal to t dot cos, integral of course will give us sine nt over n minus integral dt divided by dt is 1. That's 1. Then integral of cos nt will give us sine nt over n everything t. So this will now be the same as t sine nt over n minus, to bring out this 1 over n integral sine nt dt. So this is going to be t sine nt over n minus 1 over n into bracket. This will give us minus cos nt over n. Okay. So in this case, integral t cos n t dt will give us t sine n over n minus times minus will give us plus n times n is n squared, then cos nt. So now that we have resolved this integral, so we have to place it in the limits. Recall that this whole expression here is an is equal to this. So an therefore equal to 2 pi squared into bracket t sine n n plus cos n t is n t, sorry, so t here squared 0 to 2 pi. And once again, my previous deductions, this reduces to 0, this reduces to 0, so it's equal to 1 over 2 pi n squared into 0 is equal to 0. So an is equal to 0. So far, we have been able to deduce a0 to be equal to 1 2, an is equal to 0. So what is left is bn. So we solve for. Okay, so now to solve for bn, we have that bn same as 2 t0 integral 0 to t0 s of t sine n t dt. So once again, we know that omega naught from our previous deduction is 2 pi over t0, which is 2 pi over 2 pi is equal to 1. Then we have s of t, 2 pi is the same as 2 pi. So we substitute for these parameters. So this will be the same thing as 2 pi integral 0 to 2 pi t over 2 pi sine n t dt. So let's just truncate this. So 1 over 2 pi squared integral 0 to 2 pi t sine nt dt. So once again, you have to solve this by integration parts, and already know UV integral VDS is the same as U integral VDS minus integral du ds integral VDS ds. So here this is U and then this is V. So integral t sine nt dt is the same as U t integral sine nt dt is integral du. If U is t, du is dt. This is dt integral v sine nt dt. So this is going to give us integral of sine is minus, so that's minus t dot cos nt n integral this divided by this is 1 dot integration sine. This again is going to be minus cos n t n dt. Perfect. So this now is going to result in integral t sine n t dt is equal to minus t cos nt divided by n. Minus times minus is plus 1 over n integral nt. And this is going to give us negative t cos nt n plus 1 over n integral sine nt. So this will be minus t cos nt n plus sine nt divided by n squared. Okay? So that is the integration of t sine nt dt. So once we plug this expression into this, so dn, let's change the color. So Vn, this is Vn, 2 pi squared into bracket minus t nt n plus sine nt n squared 0 to 2. So this will be the same as 1 2 pi squared to bracket this, that's minus 1 is 2 pi cos n dot 2 pi n cos sine n dot 2 pi n squared minus 0 times this will be minus 0 divided by n plus sine 0 divided by n squared. So this reduces to 0, this reduces to 0, sine this reduces to 0, then here this reduces to 1. So that what we now have is 1, 2 pi squared into bracket minus 2 pi divided by n. So this will be to minus. This will truncate this and this and so in other words, Bn is equal to minus 1 n. So from this, can write the series so that s of t is equal to 1 over 2. So let us expand the series first. Let us expand the series. Know that s of t is the same as a0 plus summation of an cos n omega t summation bn sine n omega naught t to 1 to infinity to infinity. So since omega is equal to 1, we already established that here. So s of t is equal to a0 plus summation an cos nt summation bn sine nt to 1 to infinity here to infinity. You know, an is 0, so this reduces to 0. So s of t is the same as a0 summation n to 1 to infinity bn sine nt. So we have a0 as 1 over 2 plus minus bn is minus, so minus summation n to infinity bn is 1 over n pi sine nt. Okay. So that is the series. So based on our deductions in terms of relating magnitude, phase form, and exponential form, then the coefficients for the other forms can be derived, and I will have this. And afterwards, we could express the complex exponential form and the magnitude phase form. I think this is a good place to stop. Hope to see you some other time.